It's me again, your favorite lab partner, and I am back to be your lab partner for Simple Harmonic Motion 2. Well, let's get started. So in lab, you took all the data that you would need for this part of the lab. So a week ago or so, got all your data ready to go, and we're going to start analyzing that data here. All right, so this is basically a repeat of pendulums 1, 2, and 3 with this new data. So our goal again is to get a mathematical model and compare it to the theoretical model. And this week's mathematical model is even a little more complicated than the pendulum one. So let's see how we do. Okay, so I have the instructions open here. I have my lab skeleton open, and I also have Excel open. So if you wanted to pause the video here and get those 3 files ready to go, that wouldn't be a bad idea at all. I'll see you when you got them ready. All right, so we are going to start off by creating graphs in Excel by using our good graphing techniques we have an Excel video on those, and you practiced them already in Pendulum 2, I think. So I have here in my Excel, I have some data that I took. And so what I'm going to do right now is go ahead and make a graph with just the dots. And I'm going to be lazy though and not label it. But anyhow, what you should do here is go ahead and pause the video and create a graph for all 3 sets of your data, if you have 3, and go ahead and create those graphs now. And I'm also going to create mine. So I'll see you in a minute. All right, hopefully you have your graphs ready to go. I have mine. And so again, just a reminder, I am being a lazy bum and not doing the labels that I should be. You though should definitely do those labels. So what I'm doing right now would not be getting full credit on the lab, but I'm a lazy lab partner. Okay, so I'm going to, what I just did was clicked on my graph and pressed Control or Command C to copy it. And now I am Control V, Command V to paste it into my lab skeleton. And so right now what you would want to do is also paste your 3 graphs, remember, with labels into your lab skeleton. Why don't you pause and go ahead and do that now. All right, now we're ready to write our conclusions. Since I have just 1 graph, I'm going to write 1 conclusion, but you might have up to 3 graphs, and so you would be writing a conclusion for each graph. And so I'm looking at my graph and I'm noticing, I have dip, back up, same, up, back down. Wow, okay, so I conclude that there is no correlation between amplitude and period. So I started my conclusion off with a statement either about no correlation, positive correlation, and negative correlation. Those are the 3 types of correlation that we are studying in Physics 121. Okay, my second sentence then is going to use ideas about what are the dots doing in the graph. That's what I'm looking at right now. Okay, and so my dots are, well, identical to each other most of the time, and then some dip up or down in a random fashion. Okay, so I am making observations about what the data points in my graph are doing. Okay, and so that is supporting my conclusion. Okay, so after I write conclusions, then I'm also going to write confidence levels. I actually like to write my confidence level with my conclusion, so I would do conclusion 1, confidence 1, conclusion 2, confidence 2. I like to do it in that order because, yeah. So I am 99% confident that there is no correlation between, and I'm repeating myself, right, amplitude and period. So I'm being very formal here. I'm not saying in this graph or with this one. I'm saying between amplitude and period. So I'm taking the time to repeat what this graph is about. All right. And then I would write, why am I so confident? Well, if I look here, 1, 2, 3, 4, 5, 7, 7 of the points are identical and only 2 change. And those go, of those, 1 went down and 1 went up. That's pretty clear, no correlation to me. Okay, so I'm just being like, this is what I see. This is why I'm so confident. 7 of the 9 points are identical to each other. That is like almost perfectly not correlated. So at this time, go ahead and pause and write your conclusions for all your graphs and your confidence levels for all your graphs. And don't forget that your confidence needs to have a % number with it. Go ahead and do it now. All right, we're ready for measuring instrument uncertainty. This is identical to the pendulum lab. What measuring instruments did you use? List all of them, okay? So all of them. One mistake I see a lot in the pendulum labs is people just list one measuring instrument. Maybe it was the one I mentioned in the video, and then they don't list the other measuring instruments that they used. So you definitely used in the spring lab at least 3 different measuring instruments, okay? And by the way, reading masses off the masses themselves counts as a measuring instrument, even though that's kind of a little bit awkward. It does count as a measuring instrument. So let's just talk about that one, right? I'll answer number 2 with that one in mind. So I would say for the mass measurement, my masses on the side said like 10 grams, 1, 0, space, little g, right? 10 grams. And that it gave me to the 1 gram place. Okay, so it gave me to the grams place, to the ones place, if you want to. That's the precision that it did. Okay, so for the mass measurement, then my measuring instrument uncertainty. Uncertainty, you get to watch me just horribly type, is 1 gram divided by 2.5 grams or 0.0005 kilograms. Okay, so what I'd like you to do is pause, list all of your measuring instruments. There's at least 3. Okay, answer 2 and 3 also for those. Go ahead and do it now. All right, next is the measuring technique uncertainty. So we just talked about instrument uncertainty, now we talk about technique. You took the data for the technique uncertainty in class already, and so all you want to do right now is enter your standard deviation, follow these instructions in Excel, enter that standard deviation, and don't forget the units. Okay, and go ahead, get that standard deviation and enter it into your lab records at this time, and I'll see you when you're done. All right, the next thing we're going to do is use that standard deviation to put error bars on our graphs. So for each one of your graphs, then what you're going to do is following the inserting error bars video that we used in the pendulum labs, insert error bars for these graphs. Okay, and so what you want to do, and so you're only going to have Y error bars, and the size of your Y error bar is going to equal that standard deviation that you got just before here. No X error bars, so just Y ones, and you're going to enter them into your graph, and then you're going to cut and paste those graphs, you might have up to 3 graphs, into your lab skeleton. Go ahead and get those error bars and the graphs with the error bars, put them in there now. Okay, so me being your ultimately lazy lab partner, I haven't put my error bars in there, but I will tell you right now a few tips about drawing conclusions. So let's say that you have 3 graphs. Okay, so you want to write 3 conclusions here, and say your first graph is your amplitude graph. So for the amplitude, okay, I have done this graph with error bars. Let me see actually if I have it in another sheet. I do. Okay, so I'm going to quick paste it into here. So it'll never hurt. Okay, so for the amplitude graph, look at those error bars. Every single, even this lower one overlaps with this upper one in this little range right here. I mean, okay. every single error bar overlaps. I conclude that there is no correlation between amplitude and, oh, thanks for fixing that, and period. Okay, I kind of did that backwards. I put my reasoning first and then my conclusion second. You can write your conclusion first, then your reasoning. But remember that your reasoning should talk about whether or not the error bars overlap or not, and how much they overlap. And then also you should either say that there is no correlation or there is a correlation. So we're not going to talk about positive or negative here, just is there no, or you could even say there is a yes correlation if you want to. Okay, so go ahead right now. Let's actually just draw your conclusions for all three graphs now, and then we'll come back and do confidence together. Go for it. Okay, confidence. Well, gosh, I am 100% confident that there is no correlation between amplitude and period. Every error bar overlaps, and 7 of the 9 of them overlap completely. Like, they're exactly the same point as each other. So that gave me like huge amounts of confidence. I am uber confident, okay? So, and notice that my reason for my compliment was talking about how much the error bars are overlapping. I said like they overlap completely. Everyone overlaps. These are all good things to observe. And so what I'd like you to do right now is pause and write your confidence statements for your graphs now. All right, ready to make a cut? At this point, what we're going to do is, did you find any of your variables had no correlation? Okay, and I found that amplitude has no correlation, okay, with period. Okay, did you find any that had no correlation? Maybe your amplitude data showed a correlation, which it might, okay? Maybe you have another thing that's showing no correlation. Whatever it is, go ahead and list it here and then meet me back for the next part. Okay, you ready? Okay, so now we're going to move on with just the variables that are correlated. You should have at least one, if not two variables, okay? Most people will have two variables that are correlated. Some people have just one variable that's correlated. If you have to choose, like if you have no variables left, let's keep the mass variable, okay? Awesome. All right, so what we're going to do now is for the first kept variable, let's just say my first kept variable is going to be the mass variable. What I'm going to do is go ahead into my graph. Let's pretend I have a mass graph, okay? And I am going to do best fit. Actually, you know what, I'm going to do a linear fit, a power fit, a logarithmic fit, and an exponential fit for my mass data. And then I'm going to go back and do that for my other variable, those 4 graphs. And I'm going to export all of those graphs with the equation and r squared, okay? So into Excel, I know the instructions, maybe I'll write that into the instructions right now. Make sure your equation and r squared are visible in the graph. Okay, so yeah, when you put I'm talking too fast. Wait, coffee break. Just a moment, please. Okay, I am reset. Oh my goodness. Let's just go. Let's just pause. I'm going to pause too and make some equations and put them into mine. So go ahead and pause and do those 4 fits and paste them for 1 or 2 variables into your lab records. So you'll have either 4 graphs going in or 8. Go ahead and do that now. I'll see you in a few minutes. I am back and I have taken some really some data on spring constant, okay? So, and done the 4 fits for spring constant for this old data that I had for spring constant. you might just have data for mass. You might have data for spring constant and mass. We all might have different data, and that's actually great because you kind of want things to be just a little different between people to people so that when we're discussing like group results and things like that, we have a better discussion that way when there's a variety pack versus if we all got the exact same thing. The learning actually would be less. So the more different stuff we've got, the better. I'm a huge proponent of that. Okay, so you might notice that my spring constant graphs are even lazier than my amplitude graphs were because I didn't even bother writing a title for these. So please forgive Professor's lazy nature for that. But let's take a look. I have posted a linear fit for that graph and then a power fit for that graph, then a logarithmic fit for that graph, and then an exponential fit for that graph. So one little sweet note that I'd like to add is, you notice how huge my graphs are? I love it when your graphs are that big. I just want to show you really quick. I'm even going to take the time to make me bigger in this, but I don't know if this is even, just pretend with me that you can tell. Here, look through these. How incredibly fat and thick my glasses are, even with modern technology. So if you could pretty please make things big, that helps me so much. Thanks. Okay, so I made my graphs huge for my blind professor, and here we are. Now I'm going to look at my r-squared values. So I have 0.837 for linear, 0.928 for power, that's the current winner, 0.92, oh, it's close, but power is going to take it by a hair, and then 0.88. Okay, so power fit is going to be my best fit curve. So I'm working with my second variable here. So what you want to do right now is look at the r-squareds for your 4 fits and then write down what the name of the fit is, okay? One of these 4 names over here for your winner for both curves if you've got 2, so go ahead and do that now. Okay, now it wants us to write down the best fit from the Excel, 2.8532. And then I have x, and then I have it to a power. Oh my goodness, is that a negative? I'm gonna have to zoom in. X to the negative, oh my goodness gracious. X to the negative 0.614. Okay, and then I'm going to quick make that an exponent. Okay, so what you want to do now is to write the Excel version of the best fit curve. So that's like, oh, oops, I forgot the y equals part. I always do that. Maybe you do it too. We'll be mistakers together. Okay, but go ahead and write the best fit curve from Excel for your 2 variables. If you've got 2, go ahead and do it now. Okay, and now I'm going to rewrite it in terms of my physics letters. So in my case, the y-axis is period, which is represented by capital T. Okay, the x-axis for my spring constant is actually K. So I'm noticing I'm going to go off my screen here. I'm going to scooch over a little bit. Okay, T equals 2.8532 K to the negative 0.614. Okay, so equals what? Negative. Okay, so K is the letter of the alphabet in physics for spring constant. Maybe you have mass, then you would use lowercase m for mass here. So go ahead right now and write your best fit curve in terms of T and the second kept variable and the first kept variable. If you have 2, go ahead, do it now. All right, conclusion and confidence. Okay, I'm gonna, with first variable, I'm working with my second variable, awkwardly. All right, so I conclude that spring constant is negatively correlated with period. Okay, so that's my conclusion. And now I need to support my conclusion with a fact about my best fit curve. Okay, my best fit curve was a power function with a negative exponent. Okay, that is a curve that heads downwards. Okay, so what about your curve? Like, did you get an exponential curve? Did you get a power curve? Is the exponent on those negative? When you have negative exponents, those are curves that tend to go negative or downwards. So they have negative correlation. Or maybe you got a power function that had a positive exponent. Okay, that's going to mean a positive function. Maybe you had like a negative coefficient. Okay, that's going to do something to your function. So what I'd like you to do right now is to write a conclusion, okay, just a conclusion for right now, about each variable, and then talk about what the actual curve is doing. You can talk about the, if you had a linear fit, you can talk about, is the slope positive or negative, right? If you had the other fit, you want to talk about what their exponents are, what their coefficients are. Okay, so go ahead, pause, and do that now. Okay, ready for confidence. So my R squared was 92, so I'm just going to say 90% confident in this correlation because the R squared value was I think it was 0.9928 or something like that, which isn't incredibly great, but is good. Well, is close to 1.00. This means that most of my points did follow that mathematical model, and so most of them were definitely negatively correlated. So the R squared is really, I don't know what is your problem with that? Okay, this new blue underline, oh, it doesn't like but. Well, I'm going to keep it. Okay, so R squared tells you how many of your points are actually fitting on that model. All right, how many of your points actually fall? How close are they to this exact equation? So if all of your points are this exact equation, you'll have an R squared of 1.00. So that math model is a very good model for your points. In my case, I had 0.928, which means it's a decent model for my points. Okay, it's not amazing, but it's decent. So, my confidence is 90%. Okay, so that's what R squared does. So go ahead now and write your confidence statement. Don't forget your percent. Okay, and don't forget to talk about the R squared and how it affects your confidence. Go ahead and do that now. Okay, so we're getting close to the end of this part 1, which is the longer part, but what we've got left is you are going to now write your math models, this version, the one with the variables, into the Padlet for the class. And if you had 2 math models, you'll write both, because now you're double helpful to your classmates because you have 2 models, right? And then what you're going to do is find 2 models that are similar to yours and tell me how they are similar. Okay, let's talk about how you can tell if they are similar. The first thing is, are they the same function? So are they power function? Is yours a power? Are they exponential? Are they logarithmic together? Okay, that's really the first place thing to talk about, because if they're not the same function, then technically, according to math, they're not even similar to each other. It's like if I got a power function and owl here got an exponential, we're totally different. It's not similar at all. Even though exponentials and powers might look similar because they have coefficients and exponents, they're really not. So what you want to do is, hopefully you'll find some people with similar functions. Okay, if you can't, you're just going to be like, well, their function kind of looks like mine, even though it's different. Okay, so are they the same function? And then what you want to look at is, are the sorry, I'm in bold again for some reason, but are the coefficients similar? Are the exponents similar? Okay, this is good for hi cat, exponential and power functions. okay? Coefficients is good for logarithmic functions. Oh gosh, I thought the cat was eating my breakfast for there. Okay, exponents are similar for exponential power functions, and then or if you're for linear only, are the slopes similar? Are the y-intercepts similar? Okay, so if you, depending on what math function you have is what you can compare. So if you're comparing two linear functions, you would compare their slopes and intercepts. If you were comparing two power or exponential functions, you would compare coefficients and exponents. Okay, the logarithmic function has a coefficient, but it has what's called an argument instead of an exponent, and so that I'll just write that down. That's like what's inside the logarithmic function. So go ahead and, well, I'm just going to talk about the differences too. For the differences, again, it's the same exact things you're going to look at. Are they the same function? Do the coefficients are different? Are the exponents different? Mainly though, pretty much what you're going to do for differences is find people with functions that have different functions, right? So I got power and my friend over here got exponential, and so I would compare mine with yours. Okay, for the differences. All right. Whew. Fantastic. So math model questions are pretty easy to understand. Like overall, how well does your math model match the ones from the class? Give examples again to support your answers. The examples are huge. Yes, I make you repeat things. That's for learning. It's a learning trick. When you repeat things, when I make you type the same thing more than once, when I make you type things at all, and then I make you type it more than once, that's a big hint that it's really important, and there's a reason why she's making me repeat myself, okay? So go ahead and repeat yourself here. And then how does all of this affect your confidence in your mathematical models? Did your confidence go up? Did it go down? So here, use a percent again, because always have a percent, but also mention if your confidence has gone up or down after seeing your classmates' models, okay? Always give specific examples. So I would say, wow, my model did not match the one from the class because the only other person in class was Owl, and Owl had an exponential and I had a power. And so so those are my examples, by the way. I had an exponential, Owl had the power. Or wait, it was backwards. Owl had exponential, I had the power. Those are the examples to support the answer. And then how does this affect the confidence? Well, gosh, you know, I'm not so confident anymore. Maybe I'm down to 50% confidence because half the class got a different function than I did. There, very good. Okay, so that's the end of this helpful video. The next one is going to start with the spoiler alerts and step you through the very last part. So I'll see you there.